What if I told you that any signal you've ever seen, a sound wave, a radio wave, a heartbeat monitor, can be broken down into simple, pure sine waves? That's not a trick. That's the Fourier Transform. And once you understand it, you'll see it everywhere in engineering. Here's the challenge. When you look at a signal in the time domain like this one, it looks chaotic, right? You can see something is oscillating, but you can't easily tell what frequencies are in there or which one is dominant. And in engineering, that matters. Is this a 50 Hz power line interference in your circuit? Is this a 900 MHz carrier frequency in a mobile phone? Looking at time alone doesn't tell us. We need a different perspective. We need to look at the frequency domain. And that's exactly what the Fourier transform gives us. Let's build the intuition from scratch. Start with one simple sine wave, 1 Hz. Clean, simple. Now add another 1 3 Hz at a smaller amplitude. Notice the shape is already getting more complex. Add 5 Hz and 7 Hz. Look what happened. 4 simple sine waves combined together created something that looks complicated and messy. Now here's the key insight. The Fourier transform works in reverse. You give it a complex signal and it finds the individual sine waves hiding inside. It identifies each frequency and its amplitude. Every signal is just a recipe. The Fourier transform reads that recipe and tells you exactly which ingredients are in it and how much of each one. Now let's look at the formula. Don't panic. We'll break it down piece by piece. Capital X of F, that's our output. The signal expressed in the frequency domain. This is what we're solving for. X of T, that's our input. The original time domain signal we started with. Now this term, e to the minus j, 2 pi f t, this is the key ingredient. Think of it as a rotating phasor. For each frequency f we want to test, it spins at that exact frequency. And we multiply it with our signal. If our signal contains that frequency, the multiplication gives a big result. If it doesn't contain that frequency, everything cancels out and we get 0. The integral just adds it all up across time. So the Fourier transform is essentially asking, hey signal, how much of frequency f are you hiding? And it does that question for every possible frequency. Let's see it in action with a concrete example. Here on the left is our time domain signal. It's x of t equals sine of t plus 0.5 times sine of 3t, 2 sine waves mixed together. Now we apply the Fourier transform. Look at the right side, the frequency domain. 2 spikes, one at 1 Hz, the fundamental frequency with full amplitude, one at 3 Hz, the harmonic at half the amplitude. No more guessing. No more looking at that wiggly mess. The Fourier transform instantly told us there are exactly 2 frequencies in this signal, 1 Hz and 3 Hz, and here's how strong each one is. That is powerful. This is how your phone filters out noise from a call. This is how engineers design filters in DSP systems. This is how MRI machines reconstruct images from your body. All of it rooted in this one idea. The Fourier transform powers wireless communications, audio processing and music apps, MRI and medical imaging, JPEG image compression, radar and sonar systems. It is one of the most important mathematical tools in all of engineering. In the next video, we'll take this further and look at the discrete Fourier transform, how computers actually compute this digitally. If this helped you today, give it a like, hit subscribe so you don't miss the next one, and drop your questions in the comments below. Also, let me know what topic you need the next video on. See you in the next video.